There we go. Okay, so let's plug in some numbers. Okay, so I'll just rewrite Q from the ice equals Q from the water. And there's three regions. So if you look at the previous slide, there's three regions here where it heats up to freezing, the specific latent heat region where it's changing state, and the region here where it's heating up to its new temperature. And then Q of water is just where it cools to its new temperature. Okay, so let's look at some numbers. So we have the mass. Remember, the first region is specific heat capacity. So we have the mass of ice times specific heat capacity of ice. And then we have the new temperature that's going to be at, which is just 0 degrees. So that's the freezing point, minus, and the temperature it's currently at, which is minus 10 degrees Celsius. Okay, so that's the change in temperatures from the new temperature to the old temperature. Next, we have the second region, and that's the area where specific latent heat comes into play. And that's the mass of the ice. Remember, we're just looking at the ice here, so it's always going to be the mass of the ice plus the specific latent heat of the ice, so my slice, plus the mass of the ice. So now this third region is where it's past the freezing point. It's past 0 degrees Celsius. It's just going to heat up. And so that gives us the mass of ice times, now that mass of ice is turned into water. And so now we have to look at the specific heat capacity of water, because that is water now. That ice is now melted. It's become water, so the specific heat capacity of water, and it's at its new temperature, which we don't know, but it got to that new temperature from its original temperature, which was 0 degrees. Okay. So just let me get my pen here. There we go. Minus 0 equals. So now let's look at the heating of water. Well, it just cools down. Okay, so the mass of water, whatever the water is, times specific heat capacity of water, and then it goes from its current temperature to whatever the new temperature is. Okay. Yes. So that's our equation. That's where we start with. And now we can start plugging in numbers. Now one option you can do is just keep the variables and just make an equation with just these variables, and at the very last step plug in the numbers. Okay. But from GCSE and from previous classes, you may be used to just plugging in numbers, and it can make it much simpler in the long run. So in this example, I'm just going to substitute numbers in. Okay. And it's not good practice, so I shouldn't do this, but you should put units in all intermediate steps. I'm just going to put the numbers, okay? Because when you put units into your intermediate steps, you can see how the units actually cancel out, and you can see how the final unit comes into play, okay? But for the sake of space, and because I know many of you are in the habit of not putting units, I won't put the units for just this question. Okay, so the mass of ice was 25 grams, so we're putting this all into standard SI units, so this is 0.25 kilograms. The specific heat capacity of ice is 2,218 joules per kilogram per Kelvin, so that's what we have there. And this is just minus 10, so that's just plus 10 degrees Celsius. I told you I was going to put units. I made a mistake there, so I promise I won't do it again. So mass of ice stays exactly the same, 0.025 times the latent heat of fusion of ice, which is 334. And the units for that are, what do you think it is? I'll tell you. It's kilojoules per kilogram. Hopefully use that split second to think about what it was and to try to refresh your memory. And the final one is the same mass, specific heat, so 41. This is the specific heat capacity of just liquid water. Okay, that's kilograms, that's joules per kilogram per Kelvin. Okay, so same units as we had before. And this temperature, which we don't know. So that's our only unknown. And if we have on this side the mass of water, well, the water is 0.300 kilograms times the same specific heat capacity of water. So it's 4,178. And then we have 20 minus T. Okay. So now this requires basically to group all these together. Okay. So these three variables become 554.5. Okay. And the units that ends up being is basically degrees Celsius. So you can see a lot of the units are going to cancel out here. And what you end up with is just degrees Celsius. Okay. Next, we have 8,000. So get your calculators out and you can double check these calculations. So 8,350 plus we have 104.375 times T. Now it's good practice to keep as many decimals and as many significant figures in intermediate steps as you can. Okay, and only do the rounding at the very final step. Okay, so next we have that, and now this we have to expand. So there's two terms here. There's this term multiplied by 20 and this term multiplied by minus T. So what that gives us is 25,068 minus 1,253.4 times T. Okay, just a couple more steps. So what we want to do is isolate, get T by itself on one side of the equation. So bring this one over, and then these two guys, or these two gals, depending on how you want to call them, move over to the other side of the equation. So here we have 104.375 plus 1253.4 T equals, and all this stuff. So 25,068 plus 554.5 plus 8,350. Okay. Adding these up gives you 1,357. So let me just erase that and get my pen back out. There we go. So 1,357.775 T is equal to, we add all these up, we get 16,163.5. So T, we just divide this term by this term over here, and we get the final answer, which is 11.9 degrees Celsius. Okay? And so the key point to remember is look at these three regions. Heat lost is from one thing, is heat gained from the other thing. So heat lost by the water is heat gained by the ice. Okay, so this is all the ice material, this is all the water, and then you basically just plug in the numbers as you go. So use this equation to plug in the numbers. It can be a long equation, but you simplify it and it becomes a bit easy. Okay. Now you may have noticed that earlier in the question I was listing off the units of these constant values. So sorry, I have to get back here. All right, here we go. So when we look at these constant values, so I'll use green. Here, specific latent heat and specific heat capacities of all these values. I said the units were, for example, this unit was 2,218 joules per kilogram per Kelvin. Okay, and because Kelvin and degrees Celsius use the same scale, okay, they both increase at the same rate, the two are interchangeable. So we could also say 2,218 joules per kilogram per degree Celsius. Okay, so it's equally as correct to say both. And either way, we get this answer, which is our final answer. Okay, so hopefully that was clear to you all. Now, this is an interesting, good kind of question because it allows ways to basically find the thermal equilibrium. So find whatever that common temperature is. Okay, so hopefully that was all clear. Hopefully that was helpful.